Actually, someone asked me if it was a typo, if it was supposed to be Einstein. This is joint work mainly with Michael Green and Pierre Van Hove from, I guess he's a frequent visitor here from Cambridge. And I'm going to cover 4 different papers that are all sort of part of the same theme that they very much influenced me on. One of them is also joint with Siddhartha Sahi, who may show up in a bit. And the last one, I just actually put on the archive last night, and I hope I'll have a chance to get to that at the end. That's the only one that's purely about number theory. So I'm going to cover a few topics, mainly about small automorphic representations. I'll explain what I mean by small. And then at the beginning of the talk, I'll mention a result with Sahi about how small they can be, just to give a sort of a summary now. It's a relatively weak theorem. It says that for E6 and E7, there are no cuspidal minimal automorphic representations. The rest of the talk after that, we'll be talking about non-cuspidal ones, which are Eisenstein series. And they came up in some problems that Michael and Pierre suggested that we look at. And we looked at the 4 graviton scattering amplitude in a certain model of string theory and found Eisenstein series arising as some coefficients. And then from then, we can use the mathematics that's known about these Eisenstein series to say non-trivial things about, say, which Feynman diagrams contribute to them. And then that has to do with the constant terms of the Eisenstein series. We then talk about the non-constant terms and verify some predictions on which of them vanish. And this coincides exactly with what supersymmetry predicted. At the end of the talk, I'll turn it backwards. I certainly won't use string theory directly to say something about mathematics, but the idea is that the techniques which were used in doing the computations for the string theory, as well as the intuition of where to look for certain objects, were helpful in constructing some new types of automorphic forms. And specifically, the paper from last night on the archive proves Arthur's conjectures about the unitary dual. I'll say exactly what I'm proving later, but it proves all the spherical representations of split real groups that he conjectured to be unitary are in fact unitary. Okay, so since there are certainly some people here, say at Rutgers, are not in the math department and from the Institute, I want to say a little bit about what automorphic forms are. Apologize for being pedantic. So the context is we'll start with a real Lie group and a discrete group. And the first notion is of automorphic function. That simply means it's a function on G mod gamma. It's periodic. And then often there's a k-fixed condition. Most of the talk will have that. This is also known as spherical. The function is right invariant under a maximal compact subgroup, so it descends to looking at the symmetric space. So for example, for SL2R, this is the usual theory of modular forms on the upper half plane. And the automorphic form has 2 further conditions beyond just being a periodic function. The main condition is that you want an automorphic form to be an eigenfunction of the Laplacian and all other group invariant differential operators. And in order to make the definition of a finite sum of such, you allow for finite sum of eigenfunctions just to keep a vector space structure. And then another condition, which is automatic when it's k fixed, is that even if it's not fixed under k, that the right translates under k, which in principle could be a very large set, only span a finite dimensional vector space. That's a k finite condition. Sometimes we look at smooth automorphic forms and we can relax that, but mainly for this talk, everything will be k fixed. So in addition to SL2R, we're working on much larger groups. I want to have a slide or two just to explain how we deal with those, how we can compute with them. So we work with Chevalier groups, and these are very much like SL2. They're great for arithmetic because you can work with them over finite fields, over the integers, over the adels. So to start, we work with the Lie algebra. So there's a famous basis of SL2, and there are commutation relations, which are, of course, well known for these matrices. The idea of a Chevalier group is to start with the Dinkin diagram of a larger group, create a root system, and then assign an SL2 triple to each positive root. And then they fit together with well-understood generators and relations. Okay, and they span the Lie algebra. It's actually a bit too, we have too many generators in some sense for the Lie algebra because there are these h's here. Whoops. And the h alpha for different roots eventually become linearly dependent. So to make a nice basis, the Chevalier basis, one only includes the h alpha for the positive simple roots. But all the other x alpha and y alpha for the positive roots are included. And then from there, we can compute formally, at least with generators and relations, like we would for SL2. It's cumbersome, but you can make sense of all the important notions. You can define the real group, the real points. That's a Lie group. It acts on the Lie algebra by the adjoint action. That's the exponentiated group acting back on the Lie algebra. And then the set of integral points is nicely defined, not through the basis here up above directly, but it's defined as the stabilizer of the Chevalier basis under that action. Mercifully, this is the same notion of of integral points that came up in string theory. So it's a bit of luck, but because it could have been a little off. Now, for E6, if we were to write this out with generators and relations, we'd have to write everything with 78 generators or something. And so one thing I spent a lot of time on is I wanted to understand this very concretely. So here's how we do it. These are the root vectors. So there are now matrices here. These are 27 by 27 dimensional matrices. This is the minimal representation of E6 into GL27. So white is 0, blue is positive 1, and orange, or maybe brown to you, is minus 1. And this is explicit. You can generate everything else with straightforward commutations and exponentiate them to group elements. And now anytime we want to do some computation, we just work with these matrices directly. For E6, it clearly fits on the screen pretty well. We can see what's going on. If I were to put numbers in there, it would still fit on the screen. It makes it possible to do much larger scale computations than you can do by hand, certainly, but yet have the flexibility to see what's going on. I've now put all these online. I had a lot of help from Ross Lowther, and in fact, I really spent a lot of time on this, but once it's done, there's only 5 of these groups. I can use them forever. And it's not unfeasible to do it for E8. Then it's 248 by 248. That will still fit on the screen. So we're at a lucky time. Screen resolution is caught up to the finite number of exceptional groups. 10 years ago, this would be impossible. 10 years hence, this would be stupid. But now at least it's usable. One thing I should point out is that you don't have to worry about the structure constants. There are signs that come up in looking at the commutators of the root vectors in a Chevrolet basis. And I'm sorry to say, but a number of authors of papers in the automorphic form theory on E8 have confessed to me they ignore all these constants because there are too many to look at. So there's been sort of a tacit approximation before. But now you don't have to worry about writing down the relations and looking up in some big table of what the sign is when you have these. You just multiply matrices, and the signs come out. Okay, so another basic notion is of automorphic representation. This is not directly necessary to study these questions that came up in string theory, but it's certainly very useful. So we'll start off not looking with K here. We'll go back to G mod gamma, and we'll look at all the periodic functions which are square integrable, and we'll act on the group on the right by the right regular representation, just right translation, and decompose it. So there are, of course, a few different competing definitions, but a good definition of automorphic representation is it's an irreducible subspace of this action. Now, you may want to reduce the L2 condition. You have to sometimes when you look at Eisenstein series, but at least to give a notion, that's a good place to start. And a very nice thing, a very deep fact actually, is that if you start with L2, there's an inner product in L2. So all these representations are unitary. So you may have an abstract representation realized in a space of automorphic forms. Normally, that's a very complicated way to view the representation. But it has happened, and there'll be examples at the end of the talk. This was originally due to Birgit-Spey. She showed the unitarity of some representations which weren't known to be unitary. No one knew how to write down a Hermitian structure with a positive definite inner product, but she realized it in terms of residues of Eisenstein series. And that actually turns out that's the construction which Michael and Pierre and I were dealing with, and I'll certainly come to that later. Now, before I mention small representations, so a small automorphic representation is one that corresponds to a small real representation. I still have to tell you what a small real representation is. So one way to measure the size of a representation, these are all going to be infinite dimensional. It's a question of how infinite. There's a notion of Gelfand-Kirillov dimension. One way you can say this, and you can make this into a theorem, but it becomes clumsy, is if you realize the representation is acting on a space of functions, it's the minimal number of variables you need. There's another geometric way which is useful, and that's this wavefront set, or associated variety. So here's a way to define it. It's a subset of the duality algebra, but of course you can identify that with G, so that's not so important. And it's a closure of a coadjoint nilpotent orbit. A priori, it's sort of clear it's a union of such, and this is a theorem of Anthony Joseph. So this orbit, I keep hitting the wrong button. This orbit O, whose closure is this wavefront set, is one of a finite list of coadjoint nilpotent orbits, and that you can measure the size of representation nicely by attaching this orbit to it. So the dimension of that orbit is twice the Gelfand-Kirillov dimension. Now, how do you define this orbit? Well, you look at the annihilator ideal of the representation. Everything in the universal enveloping algebra which kills it, and that you can then view as symmetric polynomials, and then that cuts out a variety in G star. And that's this variety. So the computation of this variety can be complicated, but it's one of a list. And normally for principal series, it's the full null cone. For the trivial representation, it's 0. And that's a good example to keep in mind. And there are things in between, and that's actually pretty exotic in between. Okay, so another way, and my collaborator Wilfried Schmidt and Kari Vallone have proven some interesting results about this. If you take the character and take its Fourier transform in the sense of tempered distribution, its support is also this wavefront set. Again, that makes sense for the trivial representation. The character is trivial. So we're going to be looking mainly in between at some small ones, but not just the minimal one, which is an object that's been studied a lot. Okay, so how small can a representation be? So because there's a finite list, there's actually a gap. So it's sort of an interesting thing that here's a list of all the orbits for E6. This is the Hasse diagram. They all have labels, and there's some closure orders to them. You may notice that if you flip this around, it sort of, but not exactly, looks like it does to begin with. That's a known duality. So we're going to be looking down here at the bottom, and principal series would be up here. So this is trivial. Mainly we'll look at the three bottom ones. So here's a list of some orbits. If your eyes are sharp, you'll see I skipped one. These aren't all those small ones, but it's a representative list. And there's a gap. So the biggest one here would be 240, and between 0 and almost a quarter of the way up, there's no other orbits. So we'll look mainly at, say, 92 and 58. They're all even dimensional. That's because they have a symplectic structure. And now the first question I want to mention a theorem about is how small can a cuspidal one be? So it clearly can't be 0. That's the trivial representation. And I think this is the first theorem in this direction for the exceptional group, so it's extremely weak. It just says the minimal ones don't occur cuspidally. And their Gelfand-Kurloff dimensions then have to be the next one. There's another gap. So that gives some bound. The expectation is that in order for an orbit to be fat enough to support a cusp form, it should be distinguished, which means it doesn't intersect any proper Levis. There are Eisenstein series for the minimal ones, and those have been known for a while. And we'll be looking at Eisenstein series for all of them, or not all of them, but well, I think actually technically close to all of them. I don't know where this is from. I mean, Savin explained it to me, and for symplectic groups, there's a lot of work of Roger Howe and Jin-Soo Lee that have something like this. I believe that's where the expectation comes from. But I don't think it comes directly from Arthur's conjectures, because he doesn't distinguish the notion of cuspidality in the statement. The method of proof here is to try and mimic Piatetsky-Shapiro-Shalaika's argument that gives multiplicity 1 for GL3, or GLN. It gives an explicit Fourier expansion. And that fact relies on some character variety orbits. These will come up later. There's a transitive action on this character variety for GLN. It's like the action of GLN on the projective plane. That's not true in general for these groups. But the observation is the minimal representations, Fourier coefficients vanish off of those. And then it's almost exactly like it is for GLN for those cases. That's why I can't treat E8. Then there's no unipotent radical, which is a abelian of a maximal parabolic there. So probably something much stronger could be proven, but I don't know how. For the next to minimal ones, I can give some constraints about what the coefficients are, and there's likely multiplicity 1 phenomena for these two. OK, so that's the beginning of just an overview of the automorphic forms. Now the physicist will have to be bored for a few minutes. It's your turn. I want to discuss the problem that Michael and Pierre suggested about graviton scattering. Okay, so I'm going to say silly things. So, there's a lot of these things around, right? We're all weighed down by them, which is probably usually good. But we can't measure them. And one question is to understand how they interact. I think if they didn't interact, there might not be much to study. So let me draw a basic diagram. And this is on page 2 of Green, Schwartz, and Witten. This is a completely essential question when you have two particles. And the graviton is one of the most interesting particles because, well, string theory at least gives a method to do calculations with it. So here's two particles coming in, and then I drew this myself. And they do something, and then two other particles leave. Here, these are point particles. In string theory, the graviton is a mode of a vibrating string. So what you essentially do is you take that picture and deep fry it. And then there's some topology in it. So so there are these little strings that meet, and then they form one big string, and they break up into two and back and forth. And the topology of these surfaces is interesting. And we want to know the scattering amplitude. So the scattering amplitude means if I know what the momenta is of the particles that come in, what's the probability of having the two particles coming out at a certain momentum? And Einstein's general relativity gives an asymptotic formula in this. Well, actually, this gives a formula, but we view it as an asymptotic main term. And we're interested in the question of whether or not there are correction terms to that. That's a question that you can ask without string theory. You can ask with supergravity. But we are asking questions about string theory, and it'll be clear very shortly why, for an automorphic person, that's interesting. So we are looking at a very particular type of string theory. We're looking at type 2, and we're only looking at toroidal compactifications. Otherwise, the groups that will come up would not come up. If you compactify by Calabi-Yau, it's a completely different picture. I don't understand it at all. So we start with capital D dimensions, and we go up to 10. And there are coupling constants that define the parameters of the theory, and they naturally live in a symmetric space. The symmetric space came up first in supergravity in the work of Kramer and Julia, and then later came into string theory. Now here, there's no gamma. There's no discrete group yet. Now I want to give you a description of these groups. So here's the E8 Dinkin diagram. And here are the groups that we look at. So let's start from the bottom. There are many different forms in general of these split real groups, but they're specified by the maximal compact subgroup. And there's a discrete group here, which I'll explain momentarily. So the idea is we get the smaller groups by knocking off the nodes going from the right. Here it's D5. We get here, we knock off the fifth node. It is GL5 with a funny numbering, SL5. I don't know why. I guess I took this from my co-author who chose not to put capital L. When you knock off node 4, then it's SL3 times SL2. When you knock off node 3, then it's a little different. It's not just SL2 cross SL2. So here, when the rank of the group is small, or this dimension of space-time you compactify from is large, things are slightly off. That has to do with different types of theories. There's 2A and 2B, for example, in dimension 10. So the scattering amplitudes have to be functions of the moduli that describe the physics. And from the point of view of general relativity or supergravity, these are independent of the moduli. There's no dependence. After all, it'll be seen what I had before was a constant function. But in string theory, there will be a discrete group. Now, there's two ways to view it. One way is in terms of quantization of monopoles. But another way, which I think is easier to explain, is in terms of some dualities. So there's a torus in the compactification. Automatically from that, the automorphism group of that torus leaves the physics invariant. That gives an SLDZ. That SLDZ is, I should say D plus 1. That comes from knocking off this node on top. But then there's also T-duality. I get the letters confused. I'm told the letters don't mean so much anymore. T-duality has to do with a theory that the physics with small circles in the toroidal compactifications is identical to that with the large circles. That's why modular forms come up for SL2 when there's only a circle instead of a torus. And that has to do, that's an SODD symmetry. That's the integral points of the group when you knock off the first node. So you have in well, it's actually, well, I think that you could generate the full group possible. I don't know offhand, but you have more than just one transformation from the T-duality. It's a full SO D comma D from everything here onwards. So you have all these from the T-duality, and then from the automorphisms of the torus, you have everything else, and that covers all the whole diagram, and then you generate. I mean, it's not a priori obvious that's the full set of integral points. There is some work that some other authors have done to identify that. It gives Chevalier, that definition of Chevalier that I had before. Yeah, you might think it might be some subgroup or off by a finite index, but it seems to be exactly the same. Now, were it not, then we'd probably be seeing different answers later on in the talk. So what we're doing, in a sense, is checking that. But it's not. I mean, it's not like there's an axiom and a theorem and so forth that you can prove. I think In other words, there may be some controversy, but I believe this is widely understood, or widely accepted, maybe a better way to put it. Okay. Now here's an interesting point. This has to do with the relations among these. When I compactify, I may have a very large torus. Let's say the radius of one of these tori, one of these circles in the torus, is going off to infinity. Well, as far as I can tell, as it goes off to infinity, it might as well be a space-time direction. It's huge. So the theory in dimension D is related to that of dimension D minus 1. And this is called the D Compactification Limit. That's when you more or less knock off the rightmost node, and you look at ED as a Levy subgroup of a maximal parabolic in ED plus 1. Properties of that type will be useful later. But there are also, these other nodes have some meaning. So node 2 is the M theory node. Node 1 is a perturbative node. And Michael and Pierre had a very serious understanding of how relations go between it. That's really what we have to use about automorphic forms. We use hereditary properties. OK, so let me try and explain these coefficients. So I'm looking at the 4 graviton one. Other people look at 6. We can't look at 6. It's useful to separate it into 2 pieces, one called analytic and the other non-analytic. Non-analytic means there might be some logs. So here, ST and U are Mandelstam invariants. It's a South African guy, by the way. So these are combinations of the momenta of the ingoing and outgoing particles. There's a clear, I mean, this is already going back to the Verasoro and Veneziano-Shapiro amplitudes in the 60s. There are expressions that dictate what the structure would look like. So here, I'm glad this showed up. I made this larger so you could see it. There's a big sum. Maybe let's just look at it here term by term. This is Einstein's term. And there's some Riemann curvature tensor and some number of contractions. And these sigmas are combinations of ST and U, and there are some derivatives in them because they're momenta. And so you can think of this as being differentiated. This is the string length scale. The only thing I'm really interested in myself is this term in the middle. This is something that depends on the moduli, and that is an automorphic function. So there's 2 aspects. One is differential geometry. Obviously, I'm not going to talk about that. And the other is the automorphic control of the coefficients that multiply it. In supergravity and in Einstein's theory, these are constant. In string theory, these may be non-trivial automorphic forms. So we'd like to identify these. Yeah, so the sigma 2, so sigma 2 is s squared plus t squared plus u squared, and sigma 3 is s cubed plus t cubed plus u cubed. Okay, so we'd like to identify these. Here's what we start off knowing. Of course, they're automorphic, and the first one, which I didn't even label, is the constant function down here. And then the other terms are correction terms. Well, at this point, I don't know their eigenfunctions. In fact, they will not all be. And that's a pain in the neck, but what can you do? So we identified the next 2, and the next 2 are automorphic forms. We can say something a little about the one after it. Okay. Oh, I guess the arrows got a little misguided. And we do this indirectly. So we identify them as Eisenstein series, but it's not as if we get, we see there's a definition which writes it as a sum over a group. We only know that because we know something about their constant terms, and we know about the constant terms, and we keep doing this through a whole chain all the way down to SL2, where they do know it's a lattice sum, and therefore an Eisenstein series. And then we build all the way back up, and we get a list of things. And we have to roll out cusp-form solutions also. So now Peter asked, he's a slide ahead of me. So he asked the question about whether or not these are actually automorphic forms, not just periodic automorphic functions. So there are some differential equations. Green and Sethi and some other collaborators worked these out. I hope this is visible. It looks OK. So here, there's a little delta function here in certain dimensions that gives something non-zero. But for now, let's just think of those as being 0. Those are sort of exceptional cases. So these first 2 are Laplace eigenfunctions. This is the Laplacian in dimension D, and that's some eigenvalue. But the next one, this is a very strange equation. It's inhomogeneous. It has the square of the solution of a previous equation. Somehow these things don't come up in number theory. I don't. Yeah. But it's multiplying 0. Yeah. Well, this was already in the Veneziano amplitude, right? The zeta functions had come up way before. And the zeta functions are a hint. So actually, there was an attempt that I know Greg and Michael worked on before to figure out Eisenstein series based on the appearances of known zeta factors. But it's very subtle. It gives the right answer, but there's a factor of 2 difference or something, right? And, okay, whoops. Okay, so after this, I don't expect any reason why they'd be automorphic forms, or I can say something about it directly. Whitten pointed out that maybe the next interaction may, but we can't. We can say actually quite a bit about this for SL2 and a little bit about it for higher rank groups, but mainly, I'm only going to cover these first 2 guys. So they just stop being automorphic forms. What can you do? Maybe there are other problems that have automorphic forms. So they are Eisenstein series. Now let me go back and say something trivial about mathematics to physicists, perhaps. So what are Eisenstein series? Let me make a general definition. It'll be even more general in a moment. Let's start with a maximal parabolic subgroup of this Chevalier group. So I just mean that it contains a fixed Borel. And I'll factor it into a Levy part and a unipotent radical. In order to make the definition as short as possible, I've chosen to present it like this. I'll take the Haar measure on U, and then I'll take a point in the Levy and I'll conjugate U, its normal subgroup, and that will change the Haar measure by some constant. Well, that's a priori a homomorphism, and I'll call that delta P of L. And then using the Iwasawa decomposition, you can easily extend that to a function on the whole group. And you can do this very cleanly in terms of the Chevalier basis. When I work on these matrices for E6, it's like the norm of the bottom row of the matrix or something. Everything is explicit. And to form a maximal parabolic Eisenstein series, you take this function to a power and average it over the group. You mod out by things that are already in P because that doesn't change this value. For SL2, this is the usual non-holomorphic Eisenstein series. Sometimes you see this as a sum over a lattice. Here I have a relatively prime condition. So if it's over the lattice, there's a zeta factor. And for SLN, if you take there are many maximal parabolic subgroups, but if you take the ones for the first and last node, you get the Epstein zeta functions. So we're looking at sort of analogs of the Epstein zeta function on higher rank groups. Now, there's some papers where in the physics literature where there's an ansatz that the Eisenstein series are always lattices. Of course, you told us, thankfully, they're over groups. And you gave us a method to compute with the groups. That's very useful. But these guys are wizards with lattice sums. So it's very hard to, from the mathematical point of view, I think it's very hard to try and explain everything in terms of a lattice. You have to use the group theory. But they got pretty far. I think there was just this conference last week at Yale about Piatetsky-Shapiro's influence. And I wanted to mention something which I believe is true, and hopefully I'll be corrected if I'm wrong. He, I believe, was the first for SL2 to explain the Eisenstein series in terms of the rationals. I don't know if you may know better than me. The idea was that you take this pair Mn, and instead of thinking it as something over a lattice where you have this relatively prime condition, you look at the rational M over N. Then there's an SL2 structure that's related to a one-dimensional sum, and Langland's carried this out in general and got all these very clean formulas, which are completely decisive in many cases. And without this group structure, which you cannot directly see in terms of lattices, these computations, I think, are forbiddingly difficult. Although every time I tell a string theorist one, they do another one that I told them they couldn't do. So if your life depends on it, I guess you can do it, but it's already done. Now, there's that other type of Eisenstein series that comes from the minimal parabolic. Let me just slough over a little bit of the notation. The idea is it's like in several complex variables. The delta P before was only something in terms of one variable. Here we'll take a function which basically gives you the Lie algebra part of the Cartan of the Lie group and applies a linear functional. This rho is just a shift to make formulas nice. You sum over the whole group mod the Borel, which doesn't change H. It converges in a Weyl chamber, and it has meromorphic continuation. And the ones on the previous slide are actually specializations. This is a key idea. If you specialize to these lines, then the definitions coincide. So for example, if you take S to be 0 at -1, it's amazing that, of course, this is only by meromorphic continuation, but you get identically 1. And in fact, that's the reason why this previous statement I just made here is true. There's some inductive formula. You can always write this. If you break up this sum over mod a parabolic and then the parabolic mod the Borel, you get this is a sum of Eisenstein series on smaller groups. And on this one parameter family, you've set those things to be 1. Okay, now I want to explain the identification of these terms here. So what do these guys know? Well, they know differential equations. I just showed those a few slides ago. And they have control over the limits of these in different ranges. So they know something about the perturbative theory, the M theory limit, and the D Compactification limit is the one I described before in terms of one radius getting very large. And so what the statements they can say are, well, I know the E8 one has to have some properties related to the E7 one, but a bunch of different ones. And then the E7 ones are related each to E6 ones. When you get all the way down to the bottom of SL2, then there were lattice sums, and this was understood. So we worked piece by piece, building it back up. And now here's the table. Let's see how, okay. Relatively readable. So these are, maybe it's not worth it to explain the exact details of what these are. These are Eisenstein series on different groups. This label here is, say, a node. This means it's from the first parabolic. They started off on the bottom with, which I think, actually, a lot of this is your work too, I think, Greg, right? Greg and Shatishvili and Nekrasov, or at least one of them or both of them, identified the SL2 one. So I should give more credit to Greg. You don't? That's Mike Green. Huh? Mike Green? OK. Well, I gave him credit too before. So when you go up to, these are these two different 10-dimensional theories. When you go up to the 9-dimensional theory, you have to normalize. You add two Eisenstein series together, which each have poles, but the poles cancel. So we worked this. And then on SL5, it was again, from SL5 up, this one stabilizes, actually. But it's very peculiar. It's the same. It's the series at 3 halves, which is in the left half plane of analytic continuation. If you do it in the right half plane, the residues at different points. But there's a nice, clean family. Now, for this next interaction, it starts off at 5 halves. And then here, it's terrible. And then here, it's not so good. And here, these are the worst ones. There's 2 different series on SO55 and on SL5 at different points. And the exact right coefficients come up to kill the poles. And you look at the next term. But then after that, it's the same on the top as it was on the bottom. So if we knew the one on top to begin with, we would have just taken constant terms and checked everything fit.
What are you solving? You're solving, these are the first 2 terms, which are supposed to be eigenfunctions and have some growth properties. You're saying this uniquely determines them and you're identifying them as eigenfunctions.
OK, so what I'm saying here is that these are solutions to all the known equations. But these techniques have to do with asymptotics. OK, so there's a rationality assumption also, because they know something about the string perturbation should give power series with integral powers. And that there's an assumption that there aren't cusp forms with certain types of irrational behavior. I mean, irrational parameters. No, that's the first part. And because of that, we only need to check the Laplacian, because it narrows us down to a line. So we have a bit of a rationality assumption, which is part of it is an assumption, which I think is completely reasonable. And the other is from that, it narrows us down to not having to look at the other ones. But they do have some control over these other operators. OK, so now how to make this rigorous? Well, there could be cusp form solutions to these equations. This method can't see them at all. We're just looking at polynomial behavior in a cusp. And so we have to know there are no cusp forms. Well, sometimes these eigenvalues are negative. There are no cusp forms with negative eigenvalues. Sometimes they're positive. Now, luckily, I'm sure Michael was very happy. When I was a student here, Peter's first problem to me was to prove a lower bound on the eigenvalues for SLN of cusp forms. And of course, OK, so that rules them out for here. These groups aren't SLN. But if you knew functoriality, you could lift them to SLN, and they should be violations there. So you can more or less, I mean, you can't, this is certainly not saying you can make rigorous now because we don't have the functoriality. But in terms of principles, there are principles in place which make it, I mean, the only sort of thing that's not an obvious phenomenon is the exact size of this eigenvalue bound. And that's enough. So this is the paper, we wrote this paper about 2 years ago. I want to mention some things about the top. The rest of the talk, I'm mainly going to stick to the top where everything looks uniform. Thankfully, thanks to your help, I was able to get the colors or you were able to get the colors to come out. So these are, the terms of formulas are simpler. Here's a blow-up. I just put this in case you couldn't see the previous one, but I think it was probably OK. I want to say something about constant terms, so I might as well say something about Fourier expansions. There are a lot of ways you could look at Fourier expansions. Anytime you have a one-parameter subgroup and integral points, you could. It's useful to look at a maximal parabolic subgroup and look at the uniponent radical. Then the discrete group intersects it in a lattice, and you can try and do Fourier theory on it. So you can look at a character and just write down this integral. This is what it would be if you're an R mod z. This is how you define a Fourier coefficient. If U is abelian, then it's automatic that as you sum over all the characters, you can reconstruct the function. So when chi is trivial, this is the constant term we had before. In general, for Eisenstein series, these coefficients have not all been worked out in general. When it's not abelian, you lose information. And actually, the string theory can say something about can say something a little bit more than we can in some sense about that. What you get is you recover what you would have if you integrated out the form over the commutator. Okay, so that's just part of it, but we take what we can get. So here is something about the constant terms. Okay, so well, certainly in Langland's Springer lecture notes, I said SLN, not for the group, but for the Springer lecture notes. He wrote down a very general formula. It certainly applies to the Borel series, and then we can specialize it to those lines. And we can do this. There are big sums over the Weil group, and we find a lot of cancellations. A lot of terms drop out. To me, as a number theorist, well, OK, I know some are going to drop out. That's what happens. I don't know which ones are going to drop out exactly, but these guys do. They have it means a lot to them, which powers come up and which ones don't. And they have interpretations of it, and it's pretty striking. It's a good trick. So, and of course, this reference is out of date, and maybe there's better understanding since then, possibly. I don't know. But in the appendix on G2 and in the Eisenstein series monograph, I love this quote, that there was a calculation with the Weil group there, which is order 12. And this is evaluating the discrete spectrum coming from the Borel. But the final result is very simple. I do not know the reason. I don't know if there's any reason since then that indicates the structure. But you can imagine that if you look at E8, where the Weil group is a little bigger than 12, there's certainly no reason ahead of time to expect what cancellation would occur. But these guys had a pretty good hint as to what it would be. Not exactly. It wasn't like they could say, well, we know this from physics, and therefore this should happen. But they had analogies from physics to expect what would happen. So I think maybe the main thing we did was a computational technique to make this doable. Instead of having to look at the entire Weil group of 700 million elements, we only need to look at 240. And that's still more than 12, and it's a pain, but I mean, we're blessed to live in a time where a computer can do this very quickly. So there are perturbation expansions in string theory. These are powers of the string coupling constant, and that's more or less the GL1 factor of the maximal parabolic. And this has to be, by Langland's formula, it's a priori a finite sum. That's a non-trivial statement, because the powers that occur of this tell you what genus surfaces occur when you sum over all the possible interactions. You have to look at how many times the strings will come back and recombine. If there's only a finite number, it means at some point the combinations beyond that amount don't matter. And it's completely precise. So for example, we find this exact number. So for this first interaction here, this is the one that was the 3/2 Eisenstein series. The tree-level Feynman diagrams contribute, and the one-loop ones contribute, and it's exact. Nothing else contributes beyond it. No other Riemann surfaces. For the next one, you have 2-loop diagrams, but no 3 loops, no 4 loops. So that was something that was known for these small groups like SL2, but it wasn't I think even a conjecture, because there wasn't enough evidence for the bigger ones. And if you believe all this connection, then that's a non-trivial application of the automorphic forms to string theory. And at the same time, I think a non-trivial set of ideas coming back the other way that tells you, which cancellations may or may not occur. Okay. Now, that's the constant terms. The non-constant terms are much worse. I should say that this finiteness is really non-trivial, because the next term, the one that had that inhomogeneous equation, you can actually see this from multiplying out the other solutions and integrating back. There are an infinite number of Riemann surfaces that contribute to those. So it's special for those two. That's something about supersymmetry that protects these interactions. So that supersymmetry will have something to do with the non-constant terms. I believe that's much deeper. And in terms of physics, those are called non-perturbative instanton states. They're like exponentially damped contributions as opposed to polynomial ones. And again, they have, in some cases, very precise statements about what they should look like. They should be exponentials with like the exponential factor should have to do with the action. And there are things on the outside that have to do with the number of windings. So they see divisor functions coming up because you can wind around this torus and then around that torus. One particular type of prediction, for example, is that sometimes the perturbative formulas are exact. They predict in some cases with supersymmetry, when they're BPS states, there should be no instanton contributions. That means we should be looking for a Fourier coefficient, which is 0. So they tell us these automorphic forms have a lot of 0 Fourier coefficients. And as I'll explain soon, Ginsburg, Rawls, and Sudry had actually worked that out for one of them, but the other one we proved with some help. Okay. This is an excused absence. He's certainly right. Okay. I mentioned before Piatetsky, Shapiro, and Shalaika proved a theorem where they looked at orbits of characters. This will come up here. So this is what I mean by character variety orbit. I'll look at a character of U mod its intersection with gamma. There are many of these. It's a lattice. And now I'll take some point gamma in the intersection of the Levy with gamma. Let me see how this. Before I had some problems with this. That's why I just want to see if it's clear. Now, if I go to the formula that defined the coefficient and I just do this change of variables, what pops out is this relation. I get the Fourier coefficient for chi is related to the one for gamma chi, where gamma chi is a different character related by that change of variables. And the big difference is I take g and I translate it by gamma. So as functions on g, this orbit of gamma intersect L on the character variety determines the coefficient. Now, these orbits can be pretty hairy. Module actually has worked out a good number of these for a number of the ones we're interested in, in fact. So, and you too, I think, right? Some of your work also. You've looked at some of these orbits in a completely different language, I think. Not all the ones that maybe are necessary, but certainly I imagine there could be a lot of concrete work done with. Well, E7 certainly. No, I think E7 inside E8. Yeah. I mean, I was looking into this, but then it was clear we were just trying to show there was 0 for now. So we didn't need all that. Just sometimes for some crude properties, this discrete action, which is like a prehomogeneous vector space, can be very complicated, is not necessary. You just need to know the action of the Levy group, which is continuous. So then you ask the question, how does a Levy group act on the uniponent radical? Or it's Lie algebra. Well, a priori, it breaks up into finite dimensional representations. This has to do with the way it's graded in terms of the commutator or the coefficient of the simple root that defines it. And each of those is a finite dimensional representation. They're the ones that come up in the Langland's Shahidi method, for example, with the L functions there. They're on the back of your book. It's the exact same ones. And you can ask the question, what are the orbits? There are finite number of orbits in each of these. What are they? These can be tricky. If you look at E8 and you take node 2, this is like the action of like you look at trivectors in SL9 or something, SL8. Trivectors in SL8, and there's like 23 orbits or something. This is Windberg Popov theory. So over the integers, it's even more complicated. But we needed to know this, so Sahi and I classified what they are for the exceptional groups. It's much easier to do for the classical groups. It's essentially well known. It has a name, generalized rank theory, although I couldn't find any paper, so we had to reprove it in our paper. Peter Littleman had some computer programs that did it for the first graded piece. And then I knew that Shahidi, in matching up L functions in the Langland-Shahidi method, had an induction to reduce all the higher ones to the first graded piece. And that and some work does all of them. So this will appear in the Journal of Number Theory with that. And it was used in that result before about that there can't be cuspidal minimal representations. So this paper looks like a phone book. It's like 30, 40 pages of tables or something. But they're there, and I hope they're correct. I think they are. So we use these, and we do is we know where the characters live. And, we know how to get representatives for all of them. And that will come up with the coadjoint orbits. So here's the main theorem about the constant coefficients. So I'd like to state it in a little more generality than maybe makes sense. I want to include the constant function. These are the first three terms in that expansion. So there was the constant, that's Einstein's term, and then I had these two Eisenstein series that are labeled E00 and E10. So these are all Eisenstein series. The constant function is, well, it's technically an Eisenstein series at 0. It's a pretty complicated way to do it. It fits. And now I'll take, there are three different limits. These correspond to perturbation theory, M theory, and D Compactification to physicists. These are the maximal parabolics to the extremal nodes of the EN diagrams. And the first statement is that if I take the Fourier coefficients of the constant, they are 0 outside the smallest character variety orbit. Well, that's obvious because it's a constant function. Those are non-trivial characters. Next statement, much deeper, but was known actually. If you look at the 3/2 Eisenstein series, that's E00, there are a number of character variety orbits. There's a trivial one, and then there's the one after it, the next biggest one up. They can have in fact, those both have non-zero coefficients. But beyond that, all the Fourier coefficients are 0. Now, that's work of Ginsburg, Rawls, and Sudry. So they had I'll come more to their paper later. And then our theorem is the next statement, and it stops after this, by the way. So at the 5/2, then you look at there's a third orbit, and then beyond that, they're all 0. These are exactly predicted by the BPS constraint from supersymmetry. Now, beyond that, when they're non-zero, as I mentioned, if we can compute these coefficients, and a lot of the time we can, then they have predictions for how big they should be. They don't tell you exactly it's a Bessel function. They'll give you the asymptotics of the Bessel function. But in principle, it's probably the same information. They give an asymptotic series. So that they see the exponential and then the 1 over y terms that come up. And they get this, and they get the divisor functions too. That comes from windings of branes. So obviously, this was more of what Pierre and Michael did than me. But they sat for a while and calculated from geometry what the divisor function should be. So even if you ignore string theory, there is a method using one area of mathematics to get some non-trivial guesses about another area of mathematics. Okay, so I mentioned we can verify these. I hope that's readable. Okay, now, so where do small representations come up? Well, general yoga is that when you have a Fourier coefficient on a representation, you assign a function from the vector, and it's just a linear functional, essentially, if you evaluate at the identity. You're getting a number. It's an invariant linear functional, and there are theorems that limit which invariant linear functionals come up for small representations. The linear functional has a character to it. If that character doesn't live in the wavefront set, it has to be 0. The idea is that, well, if it's in the wavefront set, it's sort of related to something that kills it, and you sort of get a contradiction forcing there to be a 0 contribution. It's a simple argument, but technically difficult to write out. So a trivial representation is a good place to check all these statements. The wavefront set is 0, no non-trivial functionals on that representation. So we found, in looking at this, well, we were able to identify the Langlands parameters of these Eisenstein series. And when you put them in a positive in the dominant Weyl chamber, they are exactly the markings of the 3 largest coadjoint nilpotent orbits. I had that slide before with that big thing of things on top. Now, then there's a theory of Adams, Barbosh, and Vogin. And folks in Utah wrote an appendix to calculate this for us. There was just enough known to do it. They may have had to use Atlas, actually, if it wasn't known. But it was sort of clear it was in play. Because also, p-adically, the p-adic theory is more advanced, and we probably could have used that too. That says there's a way to calculate the wavefront sets of these Eisenstein series. They're exactly the dual orbits in Spaltenstein duality. Those are the 3 smallest orbits. That means our 3 terms, constant and the next 2, are automorphic realizations of the 3 smallest representations. And then I go to the phone book with Sahi, where I have a list of all the character variety orbits, and I computed which coadjoint nilpotent orbit they live in, and just matching them up, that theorem on the previous page follows. So this ability to compute the wavefront set is crucial. Okay, so I have about 10 minutes. I want to return to number theory. So now there's no more physics.
Can you explain something? I mean, you use a lot of parameters.
Yeah.
What relation is to the Arthur parameter?
So
In terms of SL2.
I think I can say something about it, but it'll be better to say it at the end because I have more Arthur examples coming up. Okay. I'm not sure I can explain even then, but I think it makes sense to try at that point. Okay, so up to now, what we have is that string theory identified some interesting automorphic forms, and it had some interesting properties it could see. I probably should have mentioned earlier that the theta function is an example of a small representation. And it doesn't have that many Fourier coefficients. It's only supported on squares. So Ginsburg, Wallace, and Sudri studied the E6, E7, and E8 examples before. So this theta function lives on a cover. That's why I didn't talk about it before. But these guys live actually on an algebraic group. And these have had tremendous impact. Hundley and Ginsburg have an integral representation of the standard L function on E6 cross GL2. It's degree 54. It's a Shimura type integral, and it uses this exotic theta function. In other words, they're using what I had before as E00, the 3 halves Eisenstein series. It's used to prove something very non-trivial about analytic continuation. It's also used, I think, from B2 to C3 or something, and there's a theta lift. It's a minimal representation, so you can play with dual pairs. There's non-trivial functoriality coming from that object. So that is an object that's been used. Witten raised the question of whether or not string theory could produce some objects which could lead to progress in the Langlands program over Q. Well, Witten also once said that string theory was successful in discovering the graviton. Of course, even though the graviton came first, but he said, well, at least up to experimental error with history, we have a method to explain it. It's a few years off. You can apply that logic here. Now, I mean, I'm sort of this is a bit tongue-in-cheek, but I think it demonstrates that string theory has that capability. It's a few years off. This was 10 years ago when these examples were done. So had this string theory been 10 years earlier, and there are reasons why it wasn't. The computer was important, but still, it's more or less, on a very large time scale, it sort of could be considered some type of experimental error. So if you're willing to do after-the-fact predictions, then you can make money doing anything. But I think you see the point that there is a construction from physics which turned out independently was used in number theory not that much earlier. So Green was looking at these objects around the same time GRS were. Okay, so what we found is for E7 and E8, we have automorphic realizations of the next to minimal one. And beyond that, physics doesn't seem, at least the physics we know, doesn't produce further ones. But the mathematics might. Right? I don't need them to, right? I have these techniques that I developed working with them, and now I'm going to apply them to some questions in automorphic forms. So here's an observation. Right? It's a calculation, but it's not that hard a calculation. These guys, E10, well, they're square integrable functions on G mod gamma. So that means that representation, this next to minimal representation, is unitary. Okay, that's a modern version of a back-of-the-envelope calculation. Took the computer to the cafeteria in Cambridge, and one day at lunch we did this. So I started thinking, well, what else can we do? So there are a number of other representations that Arthur has conjectured are unitary, and thankfully I'm going to only look at spherical ones, so the Arthur parameters are a lot simpler. I'll try and write it on the board at the end. I don't have a slide with what you asked. So Arthur conjectures you can find a number of representations that are unitary through the discrete automorphic spectrum. He doesn't tell you if they're cuspidal or not. This comes from analogies from the trace formula, but it's pretty precise. It's precise enough that you know what Eisenstein series to look at, and as long as you're not afraid of the calculation, then you just do it. It certainly seems easier than factoring an RSA modulus. So, okay, so what I'm going to talk about the rest of the talk, and this is the preprint I put on the archive last night, is applying the techniques from the physics to this. We're not using string theory to prove something about automorphic forms. I mean, you can't. You can only use ideas you get from it. And it certainly tells you where to look for examples. Okay. All right, so here, let me go back to the Eisenstein series. So and these have been looked at before by a number of other authors. This was the Borel series. It has a very clear functional equation in terms of the Riemann zeta function. You can make it explicit over other fields, but I mean, the point is that these unitary representations, or potentially unitary representations, are not representations people who work in real groups can prove are unitary. And that's a major reason, that's a major topic in that subject. So if you want to look at R, you just need to look at Q here. If I want to look at C, I look at Q adjoins square root of -1. I don't need the general number field, but I mean the mechanics are the same. So here's a really beautiful formula of Langlands that I mentioned before had to do with the use of the Adels. It's a very exact formula. This exponential here is like a power function in several complex variables on the group. And you can make this
Too much physics. A very exact formula.
very, OK. Yeah. 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 The very exact sequence. So SL2, this is y to the s plus this ratio of zeta functions times y to the 1 minus s. That's well known. Actually, I should have probably written c of 2s the way I've normalized it. OK. So to look at these residues, that Borel series specializes to the maximal parabolic series at that parameter. And it turns out all the ones on Arthur's list have this form. I noticed this recently. I mean, it's not essential, but it makes life a lot easier. So Arthur's guys are all supposed to come from inducing from maximal parabolics, from trivial. If it was sort of at the endpoint of reduction, like then there are techniques to show it's unitary, but when it's in the middle, these techniques they have as sign changes break down. So that's, at first I was afraid this would, the last time I was talking to you, I was afraid that there was some trivial reason why this would be true. But thankfully for me, it's not. Now here's a condition of Langlands. I should explain what this means. So when you specialize to this point and maybe take a derivative or a residue, when you look to leading order, you want to group these by the value of w lambda. And then when you sum over the zeta function, there might be signs that come up and you make a cancellation. So a lot of things will die out. Like when I looked at lambda is minus rho, everything dies out except the identity term. So the surviving exponents should satisfy this inner product inequality. This is Langland's L2 condition. It's because it's concentrated on the Borel. And the key point is that the inner products that come up in M, they're evaluated in the Riemann zeta function essentially at points like this. The way I set up this deformation, they're usually minus 1. So the zeta function has a pole in the denominator. So these w's, which flip any of these roots, are gone. That's why I can go down from 700 million to 240 in some case. So we want to understand the polar structure at particular values of s. As I just mentioned, if you look at s equals 0 at minus rho, it's very nice. It's a cute thing. It's like this guy who was driving in Alaska and someone volunteered to wash his window for him. But at other points, you have a big Weyl group, and the sum might not be so nice. Might be what happened a second later. So this guy. At that point, I think he hit the speed bedel. So I'm going to show you the worst case. This is a marking of an orbit that's dual to itself. It's called E8, A7. It's half the weighted marking. And so I got it down. Here, this is the case I don't gain as much as the others. I still have to deal with a lot of elements, 241,000 or so. And I have this deformation. And now I'm going to look at the images. So I have to see what survives when I take a residue. But already I've gotten rid of a lot of them because this set here doesn't have that many images. There's only about 23,000. Now we take a survey. How many of them are in Langland's range, which would give an L2 residue? Nearly all of them. Well, a good majority, almost 19,000. And I found that at least one of them vanished to order at most 3. Okay, so I didn't have to compute all of them. I just had to look at one, and I figured out what order it vanished to. That was I'm now trying to figure out the exact order, and that's probably going to run for a long time. But to prove the theorem, I don't need that. So I had to look at a bunch of sums like this. This is like a big design computation. I averaged polynomials over a symmetric set. And they don't apply on the arithmetic of the zeta function, so that is for general number fields. And the other ones, there are about 4,000 guys which violate the inequality, but I showed that each of them vanish to order at least 3. So now if I take the leading order, I've shown that this residue is L2. And this took about, it took an hour and a half because my computer has 8 cores. And I divided it up between them. But this is the worst one. There was several other days of sort of a pre-computation, mainly just to check that Mathematica was being consistent. I rewrote this in Sage. I haven't finished this example, and one of the other examples I haven't quite finished, but everything is consistent. I may run it one more time just to make sure, because it depends on it. These are all these computations are online, along with the explicit ways to view the groups. So now here we have a bunch of new small automorphic representations. Not all of them are so new. The trivial representation is on this list. This is Arthur's list of spherical ones. And this O check tells you the wavefront set. So in each time, I can tell you what the wavefront set is of these. These are the ones that Ginzburg, Wallace, and Sudry looked at. They have the minimal orbit as their wavefront set. The one after it, these are the ones that we proved are next to minimal. E6, next to minimal doesn't mean as much for E6, so I didn't include that. But the other ones are new. Now, once I have these, I can start inducing these unitary representations and make a lot more. And so here's the last slide, finished I think just on time. So these are all all the local representations of at least of split real groups whose unitarity are through conjectures. So we start with any Chevalier group. We look at its dual group. We look at a weighted marking, which this is how Deakin classifies orbits of a cojoint nilpotent orbit. And we look at the principal series for that lambda. So the markings are canonically linear functionals on the Cartan of the original group G, and you can induce a principal series there. And then we look at its spherical constituent. And the theorem is it's unitary for all these examples. Now, a lot of this was known. It was known for classical groups already by Maglan. It was known for G2 by Kim. And I mean, I've stated this for this is true. What I stated here is any field of characteristic 0. But the periodic, non-Archimedean ones were already known by Barbash and Moy. So that leaves me with only 2 fields. But I think there's still a point to doing it for R and C because I believe other methods were stuck. There are some other approaches. Atlas and also Schmidt and Valonen have a new Hodge theory approach, which is aimed at these exact objects. And they'll interpret this very differently when that finishes. But for complex groups, my understanding is Atlas can't possibly run in any human time the way it's currently designed. The computation is several orders of magnitude more than it was to begin with. So that, at least this method, says something about complex groups. So I think I went slightly over, and I apologize for that. But thanks for your time.